Hey guys, welcome back to chapter 4. We are going to continue to talk about resonance structures, and we're going to learn a tip or tool to pick the best resonance structure. Up until this point, the resonance structures that we have done have all had the same atoms surrounding the central atom. So we looked at ozone, which was OOO. And then we looked at nitrate, which is nitrogen with three oxygens around it. And that double bond bounced from oxygen to oxygen. So there was pretty much all the same no matter where the double bond was. But what if we have a structure where the atoms are not the same? So here we see three valid resonance structures. In the first one, we've got nitrogen in the middle, a triple bond with the nitrogen to the left, and a single bond with an oxygen to the right. If we look at the next resonance structure, we've got a nitrogen in the middle, but this time it's a single bond with a nitrogen on the left and a triple bond with oxygen. So those are two very different structures. And then the last structure here has a double bond on both sides. So one of these structures is the best, is the most stable structure, is the way that we would find this compound in nature, right? Formal charge is how we determine which one is the best structure from kind of a theoretical perspective. So without actually like testing the bonds, can we assign numbers to these atoms and theoretically decide which one should be the strongest one? Formal charge is the way that we do that. Formal charge isn't like a real value. It's just something we use to kind of theoretically calculate what should be the strongest one. So it's just an accounting tool. If you think about it that way, it's a way to take account of what's going on and decide which one is the best. Okay. So we're going to look at an example together. We're going to actually calculate that nitrogen oxygen one. But here's how we would calculate formal charge. So first we're going to determine the number of valence electrons in the free atom. So in each of the atoms, the nitrogen, the oxygen, we're going to determine how many valence electrons it originally had. Then for each atom, we're going to count the number of lone pairs on that particular atom. We're going to calculate the number of electrons that are in a bond, and then we're going to divide that number by 2. And then we're going to subtract the sum from steps 2 and 3. So here's kind of how that formula will look. So for any particular atom, the number of valence electrons minus the number of electrons in a lone pair plus half of the shared electrons. So the best way to do this is really just to dive into an example. Okay. So in this example, we are going to calculate the formal charge on each of the atoms in this first structure. Okay. So I'm just going to kind of make another kind of secondary table. So let's start with this first nitrogen. So, oopsies. The number of valence electrons that nitrogen brings would be 5. The number of lone pairs on this particular nitrogen, he's got 2. So number of lone pair electrons, 2 electrons. And then number of shared electrons. So he's sharing a lot. He's sharing 2, 4, 6. So he's sharing 6. And then eventually we're going to take 1/2 of that. That's going to go into our formula. Okay. So I'm going to do step 4 up here at the top just so we have some room. So we're going to take the valence electrons, 5, and then we're going to subtract that from the number of lone pair electrons, which is 2, plus 1/2 of the shared. So half of 6 is 3. So we've got 5 minus 5. Our formal charge on that is going to be 0. That's actually a good thing. Okay. So let's do the formal charge on this central nitrogen. So again, I don't know how I did that. So let's do 5 valence electrons. How many lone pairs does that central nitrogen have? Yeah, he's got 0. Number of shared electrons. So he's sharing 8 electrons. And then again, eventually we're going to take half of that. So up here at the top, we're going to have 5 valence minus number of lone, which is 0, plus half of the shared. So that would be 4. So 5 minus 4, it's got a formal charge of 1. And then for this oxygen right here, oxygen has 6 valence electrons. Number of lone pairs, he's got 2, 4, 6 lone pairs. And then number of shared electrons, he's sharing 2. And then again, eventually we're going to take 1/2 of that. So calculate the formal charge for oxygen is going to be 6 minus 6 plus half of the shared is 1. So 6 minus 7 is a -1. Okay. So why don't you guys go ahead and pause the video and see if you can calculate the formal charge for the next 2 structures. So formal charge on each of the atoms for the next 2 structures. All right, so I'm going to go through this pretty quickly. Hopefully you have your work and you can just follow along with me. So nitrogen has 5 valence, 6 lone pair, sharing 2 in the bond. So we've got 5 minus 6 plus 1, which is 7. So 5 minus 7, that's a -2. Central nitrogen is going to be 5 valence, no lone. He's sharing 8 electrons. So 5 minus half of 8 is 4. So 5 minus 4, that's going to be a 1. And then oxygen has 6 valence. He's got 2 lone pairs. He is sharing 6 electrons. So we're going to take 6 minus half of 6 is 3, 4, 5. So 6 minus 5 is going to be 1. And then in our last structure here, nitrogen is 5 valence. He's got 4 lone. He is sharing 4 electrons. So 5 minus 4, half of 4 is 2, so 4, 5, 6. So 5 minus 6 is -1. This guy is 5 valence, no lone, sharing 8. So 5 minus half of 8 is 4. 5 minus 4 is 1. And then this oxygen here has 6 valence. He's got 4 lone pairs. He's sharing 4 electrons. We're going to take half of that. So 4 plus 2, 4, 5, 6. 6 minus 6 is 0. Okay. Awesome. We have assigned formal charge. What does that even mean? So choosing the best structure. So there's going to be 3 kind of criteria to choose the best structure. And I would say this list is a hierarchy list. Like we start at the top and it's more important at the top, less at the bottom. So the first one is the best structure is the one in which the formal charge on each of the atoms is 0. So if we had a case where formal charge on all of the atoms was 0, that would be the best structure. We've got a couple zeros in our example, but not all of them are 0. So we need to kind of keep going here. If no such structure can be drawn, the best structure is the one where most of the atoms have a formal charge that equals 0 or as close to 0 as possible. So looking at our example, I see that this first structure and this last structure have zeros in them. So right away, I can probably get rid of this middle structure. It is probably not the best. Number one, there's no zeros in the formal charge. And number two, it's got a 2 in there. It's got the biggest number. So middle structure, definitely not the most stable. Okay. The first and the last, so we do have 1 0 here. And then we've also got a positive 1 and a negative 1. So one of those structures is likely to be the best. And then the last one is if any negative formal charges should be on the atoms that are the most electronegative. The most electronegative. So going back to our structure, in this first structure, we've got oxygen with the -1. In this last structure, we've got nitrogen with the -1. So we want that negative value to be on the most electronegative atom. So then you would go to your electronegativity chart, which is something that would be supplied. Oxygen has an electronegativity of 3.44. Nitrogen has an electronegativity of 3.04. So it looks like oxygen's electronegativity is higher than nitrogen. So we want the structure that has the negative formal charge on that oxygen. So the best structure would be this first one. We can get rid of the last one now. So the best structure for N2O would be the triple bond between the nitrogens and then the single bond with the oxygen. So again, assign formal charge, use this criteria to pick the best structure. I'll do another example in a video, but I hope you guys found this helpful.